All right, let's get into one of the most mind-bending but also one of the most important topics in all of science, quantum mechanics. This is the science of the very, very small, and trust me, its rules are about to challenge pretty much everything you think you know about how reality works. So, to get our heads in the right space, let's start with the really famous thought experiment. It's called Schrödinger's cat. Imagine a cat in a sealed box with a poison that might be released at random. Until we actually open the box and look, quantum theory says the cat isn't just dead or alive. It's in a state of being both at the same time. Yeah, I know. And that paradox right there, that's the perfect intro to the bizarre world we're about to dive into. You see, for centuries, we thought the universe ran like a perfect, predictable machine. On classical rules. If you throw a baseball, you know exactly where it's going to land. But around the turn of the 20th century, physicists discovered that when you zoom way, way down to the level of atoms, the world stops being predictable, and it starts getting really, really weird. The rules just completely change.
So, where did these old, comfortable rules first start to break down? This wasn't some philosophical debate either. It was a full-blown crisis, born from real experiments that were giving results that just made no sense at all.
Okay, so the first major crack in the old physics came from something called blackbody radiation. Basically, it's about the light given off by a hot object, like a glowing piece of metal. Now, the old rules predicted that as an object got hotter, it should start blasting out an infinite amount of energy in the ultraviolet range. They called it the ultraviolet catastrophe, and it was obviously wrong. I mean, your oven doesn't create a black hole when you turn it on, right? The math just didn't match what was actually happening.
So in 1900, a physicist named Max Planck came up with a radical, almost desperate solution. He asked, what if energy isn't some continuous flow, like water from a tap? What if it can only exist in tiny, individual packets? He called these packets quanta. Honestly, it was a wild guess, but when he plugged that idea into the math, it worked. It perfectly solved the blackbody problem.
And that one idea, that energy comes in packets, just blew the doors wide open to a whole new understanding of reality. And the rules of this new quantum reality, well, they go from being a little odd to being genuinely strange.
First up, we have superposition. This is a concept that just completely breaks our everyday intuition. It's like saying a single electron isn't in one specific place, but it's existing in a cloud of all possible places at the exact same time. It's only the act of looking at it or measuring it that forces it to choose and pop into a single location. And then there's entanglement. This is where you can link two particles in this really deep way, where they essentially become a single system, no matter how far apart they get. So if you measure a property of one particle right here on Earth, you instantly know the state of its partner, even if that partner is on the other side of the galaxy. Instantly.
And let me tell you, this was not an easy concept for physicists to accept. The great Albert Einstein himself was so bothered by this idea, this instantaneous connection that seemed faster than the speed of light, that he famously called it spooky action at a distance. He was convinced it had to be wrong. But guess what? Experiment after experiment is proven that this spooky connection is very, very real.
But okay, it's one thing to have these bizarre theories. How can anyone actually prove that these weird rules were really happening and not just some fantasy in the math? You have to be able to show it in a lab, right?
Well, it happened. And it happened almost by accident, in what turned out to be one of the most important experiments in the history of physics. Back in 1922, two scientists, Otto Stern and Walter Gerlach, weren't even trying to prove quantum mechanics. Actually, they were trying to poke holes in it. So their experiment was pretty simple, in theory. They shot a beam of silver atoms through a special kind of magnetic field and onto a detector screen. Now, based on all the classical physics they knew, they expected to see a continuous, blurry smudge, because the tiny atomic magnets should have been oriented every which way. But that is not what they found. Instead, against all expectations, they saw two distinct, separate dots. That's it. Nothing in between. The result was a complete shock. So what did this mean? It meant the atoms could only be in one of two states. Let's call it spin up or spin down. This property, which we now call quantum spin, was quantized. It wasn't like a dial you could turn smoothly to any position. It was a switch. It could only be on or off. Stern and Gerlach had accidentally found concrete, undeniable proof that the universe, at its very core, is quantized.
So for decades, we used this fundamental knowledge to understand how things work, and that led to amazing inventions like lasers and transistors for computers. But today, we are right in the middle of a second, even more powerful revolution. We're not just understanding the quantum world, we're actively controlling it.
This slide really shows the crucial shift. The first revolution, let's call it Quantum 1.0, was all about using the collective effects of trillions and trillions of quantum particles. But Quantum 2.0? That's about reaching in and manipulating individual atoms one by one with incredible precision. We're directly harnessing all their weirdness.
And all those bizarre rules we talked about before, they're not just scientific curiosities anymore. They are the actual engines of future technology. Superposition lets a quantum bit, or qubit, be both a 0 and a 1 at the same time, which gives it immense information-holding power. Entanglement links those qubits together to perform calculations that are impossible for normal computers. And other strange rules even allow for things like fundamentally unhackable communication.
So this is really why it all matters. We're moving from just observing the strangeness of the quantum world to actively engineering it. We are literally harnessing that spookiness to build computers that can solve problems we can't even dream of today, and to create communication networks that are secure because the very laws of physics make them that way.
But where does all this lead? I mean, for all its incredible success, quantum theory is still incomplete. And it's pointing all of us toward the single biggest unsolved mystery in physics today.
Here is the grand challenge. Quantum mechanics is our perfect theory of the very small, but it doesn't work with Einstein's general relativity, which is our perfect theory of the very large, of gravity, of space and time. The two sets of rules just flat out contradict each other, and for a century, physicists have been desperately trying to unite them into a single theory of everything.
A huge part of the problem, as this quote gets at, is how they each treat time. In the quantum world, time is kind of like the steady, constant ticking of a clock for the whole universe. But in relativity, time is a dynamic fabric. It can stretch and shrink depending on how fast you're moving or how strong gravity is. These two ideas are just fundamentally incompatible ways of describing the same universe. And this is where the story comes full circle in the most incredible way. To try and solve this grand mystery, to find a theory of quantum gravity, scientists are going back to the very experiment that started it all. They're designing modern versions of the Stern-Gerlach experiment, but instead of measuring atomic spin, they're trying to see if gravity itself is quantized.
Which leaves us with this final, tantalizing thought. The simple, elegant experiment that first peeled back the curtain on the quantum world 100 years ago, could it really be the key to unlocking its final, deepest secret? And maybe, just maybe, reveal our ultimate understanding of the universe itself?